In this video, we'll move into section 2.4 and formally introduce the derivatives of the trig functions. But before we jump right into the derivatives, we actually have to go backwards and first discuss some limits. So, we'll get some good trig practice here. We actually haven't had too much trig practice up to this point. I gave you some reminders of trig functions, but again, so far we've kind of avoided them. But the first thing, again, starting with limits, is to realize our limit techniques haven't changed. Just because we're introducing the trig functions, we still have all the same different properties. So I'm going to jump right into a problem. I'm going to ask you to evaluate a limit. Let's start off, number one. Let's take the limit as x approaches pi over 6 of 10 cosine 2x minus cosecant x. Well, what are our limits? What's our approach? The first thing we're going to do, we're going to try plugging in. And unless we get into any other trouble, that's what our limit laws give us. I mean, there's two pieces. You could take the limit of each piece separately, subtract the results. This extra multiplier of 10 go out in front. I mean, we could keep breaking it down, but all those limit properties just talked about plugging in. So if I plug in, I'm plugging in. That's where I drop my limit notation, everybody. 10 cosine 2 times pi over 6. 2 pi over 6 will become pi over 3 minus cosecant of pi over 6. You'll notice this is in radians. We need to expect that, everybody. I'll show you why that is in a few minutes, but that's one of the first things. In calculus, there basically is no degrees anymore. When we're talking about angles, we need those angles measured in radians. So we won't get x, or even if it's theta. The next problem I'll use theta instead of x, but it's always going to be in terms of radians, not degrees. Now, of course, you could think in terms of degrees. Pi over 6 is 30 degrees, so you could think that way, but you're going to need to make that little conversion yourself. And it's perfectly fine to go that way, but just realize the situation is it would be given in radians. Okay, I'm not done here. Because again, we can definitely do better than this. Cosine of pi over 3, now that's 60 degrees. Well, that should be a known trig value. Cosine of 60 degrees is 1/2, so I'm getting 10 times 1/2. Minus cosecant of pi over 6. Well, off on the side, I'll remind you that cosecant is 1 over sine, so 1 over sine of pi over 6, 1 over sine of 30 degrees, and sine of 30 degrees is 1/2, so 1 over 1/2 will make that a minus 2. 10 times 1/2 is 5, 5 minus 2. This would have a final answer of 3. Okay, let's just do one more quickly. Number 2, let's now take the limit as x approaches pi over 3, and I want to use theta here. Theta approaches pi over 3, and we'll look at sine of theta minus theta all over tan theta plus 1. Now this one looks a lot uglier. Yeah, subtraction, addition, but there's also a fraction. We've got top and bottom. But again, all those limit rules still point to just plugging in. Now we've got a little bit more to worry about. When do we get into trouble with limits? Well, no piecewise. We could do piecewise functions as well, and those always lead us with a little bit of question, a little bit of, well, what about the border points, the changing values? But here, we've got a denominator, so that basic situation, we can't divide by 0. But for any k over 0, that still is going off to infinity. 0 over 0. That's going to be the main point in just another couple of minutes. But this one at least looks like a little possible trouble, but I still try plugging in. Sine pi over 3 minus pi over 3 all over tan pi over 3 plus 1. Again, I could do better here. Right now, these situations just like these here, that's like leaving the square root of 9. We can do better than that. If it's an ugly angle, it's not a reference angle, well then we would leave it. We wouldn't want our calculator to give us ugly decimals, but these are known values. Notice I plugged in, that's why I dropped my limit notation, and now I'm just cleaning up. Sine of pi over 3 is the square root of 3 over 2. And then the pi over 3 is still just there. Tangent of pi over 3, well, I have to do sine of pi over 3 divided by cosine of pi over 3. Sine of pi over 3 is rad 3 over 2. Cosine of pi over 3 is 1/2. So I would get this divided by this, and that would just be a rad 3. And the plus 1 is still there. And this is still an ugly answer. Fraction minus a fraction can get a common denominator. Dividing by this. I mean, there's still a lot of cleanup. But just the second problem is still just to point out we're still plugging in unless we get into trouble. And even though I might be able to make this answer look a little bit prettier, it's going to be an ugly answer. I mean, I've got a radical 3, I've got a pi, nothing is going to combine with those things. So this is going to be a pretty messy answer no matter what. So I'm just going to stop right here. So trig functions, we might get lucky and we get nice things that simplify and clean up nicely. We might not, but the first point is once again still. Taking a limit, we start by plugging in. But now in number 3, we're going to run into a little bit of a problem. I'm going to give you the limit as theta goes to 0 of sine 7x divided by 2x. And if I just plug in right now, plug in 0, oh, I'm sorry, I use theta here. I'm so sorry about that, everybody. That'll be sine theta over 2 theta. Sorry about that, everybody. So I'm using theta as my variable, sine of 7 theta over 2 theta. If I just plug in 0 for theta, 7 times 0 is 0, sine of 0 is 0. 2 times 0 is 0. We're in a 0 over 0 situation. So just like we saw back in chapter 1, 0 over 0, this answer could be absolutely anything. So what we're going to have to do here is we're going to have to manipulate. But unlike in chapter 1, how do we manipulate? We saw different situations. We factored when we could. We used the conjugate with radicals. We cleaned up complex or compound fractions to simplify the fractions. We had some algebraic techniques. But now with trig functions, we're going to learn 2 identities. And we're going to use these identities. We're only going to learn 2. There are lots and lots more. There are other techniques because there's lots of other trig integrals that trig limits that do give us these 0 over 0s. So we would need more techniques. But any problem I give you could be solved using these 2 limit identities. The first one is the limit as u approaches 0 of sine u over u. Now, if you just plug this in, it's going to be almost the same thing we had here. U goes to 0, sine of 0 over 0 is a 0 over 0. But not all 0 over 0s give us the same. If it is exactly this limit equals 1. I'm going to come back and demonstrate that. I'm going to prove that, sort of informally, but I'm going to prove that result for you in a minute. But for right now, I'm going to show you how to use it, okay? But I'm secondly going to show you, so these are trig limit identities. These are going to get us out of trouble when we get 0 over 0 with trig functions. So that's the first one we're going to use, and we're going to use that one quite a bit. Number 2, I need to at least point this one out. This one gets used like twice, but still, often enough, we need to point it out. You may ask why I'm using u here and x here, and I'll explain that in a moment as well. But first, this limit is as x goes to 0, cosine x minus 1 all over x. If you plugged in, you get cosine of 0, which is 1. So 1 minus 1 gives me 0 over 0. This is another 0 over 0, but this one, the answer is 0. So again, just from these two identities, 0 over 0 can take us anywhere. This 0 over 0 takes us to 1. This 0 over 0 takes us to 0. But these are the two identities we're going to need. But the reason I used a U here, we're going to use this one more frequently. The key to this identity is that whatever the angle is inside the sign, you have that exact same thing in the denominator. So that's the key. Some people see this, they come right back to here, and they go, oh, look, it's sine 0 over 0, that equals 1. No, 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 no. It's not sine 0 over 0. It's got to be exactly this limit. Whatever the angle inside the sign, that exact same thing in the denominator. So that's the trouble right here. I've got a 7 theta inside the trig function, and I've got a 2 theta in the denominator. So how do we use this? Well, right before we use this, let me show you something that is definitely not true. Okay, everybody, this is not correct. People say, oh, okay, these need to be the same. Let me factor the 7 out. And now they go, hey, there it is. There is this identity. So this becomes 1, and 7 over 2 times 1 is 7 over 2. And they get that answer. And I have to be honest, this is particularly frustrating because this is the correct answer. But this is garbage work. That is absolute nonsense, everybody. So by getting the right answer, that's not enough. And we've mentioned that before for other situations. This is not just a class about right answers. It's about the work that gets you to that answer. So this is garbage algebra. You cannot factor out from inside a trig function. For our purposes, essentially, what's inside a trig function is completely stuck. So we can't touch that. That is not a legitimate move. So what is a legitimate move? The key here is, again, manipulation. I need these two pieces to be the same. So from what I just said here a moment ago, you can't play or touch with this piece, so you gotta manipulate this piece. For this identity to work, you have a 7x inside the sine function here. Well, this needs to be a 7x right here. How do you do that? Well, some people just go, hey, this needs to be a 7. I'll multiply by 3.5. And whatever I multiply on the top, I multiply on the bottom. So some people, they see it that way. So that's their manipulation. Others, if you don't like the decimals, I intentionally picked one. Like if this was an 8, 2 times 4 gives you 8. That's an easier one to see. I picked one that was a little tougher. Some people see it with the decimal. Other people see it as multiply top and bottom by 7 halves. 7 halves times 2, the 2's would cancel, and then you get the 7. 3.5, 7 over 2. It's the same thing, everybody. So you're really doing the same thing. I will show you a second option in a moment. But now this works. This 3.5, we can't ignore it. It's still there, technically. But I've got my sine 7x. But now this 3.5, I'll actually multiply. I don't want to compare too strongly to what we did with conjugates, but it is a little similar. We recognize the conjugate, but we couldn't just multiply the top or the bottom. We had to do both, but we actually only multiplied the conjugate pair. So here, technically, we're multiplying top and bottom. There's a technicality on the top, but on the bottom, I'm going to literally multiply and get my 7x, and now this matches. So now, the 3.5, some people like to show they take it out in front and they're pushing it along, but the 3.5 is still there, and now this all goes to 1 because of this identity. And again, that's why I said before, this was the correct answer. Some people see it as 3.5, 7 divided by 2, it's the same thing. Before I go back and prove this and we get more practice, I just want to come up here and show you one slight alternative. Some people don't like the fractions or decimals up here, so one slight alternative. You have a 2x, you need a 7x. 2x is 2 times x. Push that 2 out in front. Whether you want to push it out in front of the fraction, it's still in the denominator, but create a little space there. So now you've got a 2 that's kind of floating, and you've got an x, or technically a 1x. Well, how do you turn a 1x into a 7x? You multiply top and bottom by 7. But now, instead of just doing top and bottom here, I'm going to do it slightly differently. I have to multiply top and bottom, so the top has to be there as a technicality. The bottom, I'm going to immediately put that 7 right there where it needs to be. So now with this grouping, now it's the 7 and the 2 that's kind of floating out in front as a multiplier, so that that is still there as a part of my answer. And now the limit, and there it is. Sine u over u as u goes to 0. Some people like to literally make a translation. Let u equal 7x. And then if u is 7x, as that goes to 0, I'm sorry, I did it again. I have thetas here, and then I wrote x's here. I'm so sorry about that. Let me just make this an x this time. Again, don't let the variable bother you. I'm such a creature of habit with x. I apologize that I've forgotten. I've got thetas and x's mixed here. That's a theta. That's a theta. But still, all the same result. Don't let the variable bother you. It's over theta, so the variables are theta. Now it's over x, so the variable is x. But essentially, this is the exact same problem that we started with. But now you've got your sine u over u. Some people like to write that out extra. You don't need to. I mean, again, some people point to this, but this is exactly what this limit is using. The exact matching angle and denominator. So sine of that u over u as u goes to 0. That's the secondary part. Don't forget about this. That gives you the 7 over 2. And here again, 7 over 2 times 1, right? The 7 over 2 is pushing along. This becomes 1, so 7 over 2 times 1, and there's that same answer. Saw it here in a completely bogus wrong way, and then slight different variations. You're essentially doing the same thing here. Some people kind of like hit it all at once with this approach. Other people kind of break it up to make nicer, clean numbers to multiply through. But either way, it's basically the same thing. Okay, so before I keep going, we're going to get several more examples of how these identities can help us. But again, let's go backwards for a moment. Let's focus on this a little more. Let's see why this is true, get a little bit of a proof, not exactly, more of a demonstration, I should say, about why this is true. And that'll point out why everything needs to be in radians. Because this is the key. This identity, and same thing here, this also needs radians. And these two limit identities are going to form the foundation. These two identities are going to form the foundation of our derivatives of trig functions. So if these two identities rely on my angle being in terms of radians, then all the derivatives that follow need the angles to be in radians. So let's go to our next page. So why is this true? We're going to see this through graphs. So if I graph y equals x, I'm going to grab the easier one first. If I graph y equals x, I would have this line. Y equals mx plus b, b is 0, m is 1, and this is that perfect line that cuts through the first and third quadrants. Literally cutting these in half, 45 degrees here, 45 degrees here, because you have that perfect up 1 over 1, up 1 over 1 slope. So that is the y equals x graph. But now I'm going to use my red pen, and I'm going to graph the y equals sine x curve. And this is what's interesting, everybody. If I graph y equals sine x, there is my sine curve. my typical sine curve. And if you remember your sine curve facts, high value of +1, low value of -1, reaches its first peak at pi over 2, 90 degrees, and then 180 degrees back to the x-axis, 270 at its minimum, 360, you've completed a cycle. And we could do things in the other direction as well. And come back here for a moment. My graph's not perfect. I probably should have extended this a little bit. But pi over 2 is approximately 1.5. So this graph should, again, just be a little bit higher than the y equals x line right here, and should be a little bit lower than the y equals x line right here. But in this region right here, as x approaches 0, what can you say about my red line and my black line? The red one is y equals sine x. The black one is y equals x. And as x approaches 0, so again, from the left, from the right, we're in this ballpark on the x-axis. And if you look in that vicinity, can you even see a separation from the black line to the red line? They completely overlap in here. I mean, engineers actually use this as a fact. If you are close to 0, sine x is approximately the same thing as x. Let me even show you that quickly on my calculator. As long as I am in radian mode, so let me make sure I flip over and go into radian mode. Now, look at things like sine of 0.1. The answer is almost 0.1. Look at that, 0.0998. Round off to almost any decimal place, and you're going to have to bump that up to 0.1. If you have sine of 0.01, I mean, look at that. Again, that's even closer to 0.01 than 0.1 was to sine of 0.1. The closer you get to 0, the closer the sine value at x is to that exact x value. That is a really, really neat property. Now, again, for us, this is just why this answer equals 1. Essentially, you're dividing something by the exact same something. So essentially, it's like these are canceling out. Now, that doesn't happen anywhere out here or over here. It needed this exact window. And the second thing, the only reason that this worked is because I used radians. If I keep this scale, and if I do this in terms of degrees, I have to go out 90 degrees to get to this point. So here's x is 1, 2, 3, 4, 5. I got to get out to 90. If I do y equals sine x in terms of degrees on this scale, I'm essentially just getting a flat, dead, straight line. You wouldn't even notice it in your window, and there would be no similarity between the y equals x and the sine x curve. Again, you would have to go to 90 degrees, 90 of these dashes, just to get to that first peak. So that's why we need radians. Okay, so a nice little demonstration, like I said, a little reinforcement on why that is true. But now let's get back to the practice of using it. So sticking with those directions, number 4, I only want to do a few more. The point of this section, we still are getting to the derivatives of the trig functions, and that's still the main point. But you should expect a couple of limit problems with trig functions on your second test. A couple. So let's get a little more practice using those identities. So let's look at number 4. Let's look at the limit as x approaches 0, and let's look at sine of 9x divided by sine of 5x. Still think about plugging in, but now you get sine of 0 over sine of 0. So we're once again in 0 over 0 trouble. Again, I'll remind you directions. That's all it says. Evaluate this limit. So we have 0 over 0. And this is, again, one of those really, really annoying aspects. People get the right answer with all the wrong work. So I got to see a little something to make sure that you're doing this in the right way. Because just like I mentioned back here, people in a non-algebraic way, completely nonsense way, pull a 7 out when they can't, use an identity that doesn't apply, and then luckily get the same answer. This one's even worse. Some people just blindly cancel. They just go, hey, SIN crosses off with SIN. That is garbage nonsense. You can't cancel the letters SIN by themselves because the letters SIN mean nothing without the angle to go with it. So the only way to cancel these is by canceling all of this at once, and these are unlike terms. This at this point is like canceling the square root of x plus 1 and the square root of x plus 2. They have similarities, but they'd only cancel if they were perfectly the same, and that's the same thing here. So that's garbage. People cross off SIN, cross off x and x, and get an answer of 9/5. See that that matches the back of the book, and they feel good. So be careful with that. Secondly, other people still just plug in and just think it's 0/0, and that automatically this identity applies. It doesn't, not yet. This is not sin u over sin u. It's got to be sin u over u. We will use this in a minute, but we're not ready yet. It's not ready in this exact form. And the last thing is people still factor like the previous. They pull the 9 out in front, they pull the 5 out in front, and then yes, sin x would cancel with sin x because they are perfectly identical, but once again, you did bogus algebra. You can't pull the 9 out in front, you can't pull the 5 out in front. Go back to this one, right? Remember how this works. The 10 is the multiplier out in front, the 2 is a multiplier just on the inside. You can't bring this 10 on the inside. You can't pull this 2 on the outside. You have to leave it exactly the way it is. So that's what we're stuck with here. Okay, so how on earth am I supposed to apply this identity to this? The key here, which again, experience is a huge part of this, everybody. The key here is that I'm showing you this as an idea that you can mimic. What both of these are missing, they need to be treated separately, and they both need the plain variable beneath them. We need to treat this problem like two of these problems. So the way to start that is I'm going to divide both top and bottom by x, or multiply top and bottom by 1/x. It's just like everything else. I can't just do it to the top or the bottom. I have to do it to both. And this is great because both of them need it. This looks like I took something that wasn't that bad and made it into this big, ugly fractional mess, but this is much better. Because now I could look at this limit of the top, and by the top I'm thinking of this whole fraction, limit of the bottom, again, this whole fraction. And both of these are so close. They're not perfect. I'll grab my red pen because they both need a little something. Sin u over u, well, this needs to be a 9x. So I'll do a 9/9. And now I can finish this top one. Similar on the bottom. This needs to be a 5x to match the angle here. Well, I can't just make it a 5x. I need to multiply the top as well. So I'm technically doing these, and some people like to write this as a separate limit, this as a separate limit, get your answers, and then divide those two answers. That's fine, but there's no harm doing it the way I'm doing it here, because now it's all grouped correctly. Here, the 9 pushes along, and there's your sin u over u. So there's a 1 as u goes to 0. Over 5 pushes along, sin u over u as u goes to 0 is 1. So 9/5 for our final answer. Let's keep going. Couple more. Number 5. Let's take a look at the limit as x approaches 0. And let's look at sin x, cosine x, minus sin x, all over x squared. Well, here, Couple little different things people do. Some people are jumping to this, but it's still not perfect. People kind of see this and they want to separate. But in this one, we're actually going to need both. We still would start by plugging in. Sine is 0, cosine is 0, minus sine is 0, all over 0 squared. 0 times 1 minus 0 is 0 over 0 squared. It's another 0 over 0. But now we have to realize that we can factor. That how are we going to make those limits apply, those two identities? Which one? Well, sometimes we have to manipulate. So sometimes we just got to try something. And I'm going to try a GCF. I notice this piece and this piece, they both have signs, so I'll pull that out. And now maybe you're starting to see it, you're starting to get closer. How I did this one, I ended up breaking it into two big division problems, did each limit separately, and then divided the answers. Here, I'm going to break this into two multiplication problems. Look at the top. Look at these two pieces, and then look at what you have in the bottom. Realize you need an x here, and you'd also need an x here. So treat x squared as x times x. So now take this first piece from the top with this first piece from the bottom, and that becomes sine x over x, times the second piece from the top over the second piece from the bottom, and now you're directly applying both of those limit identities. The limit as x goes to 0, this one is perfect. Sine x over x. So that becomes a 1. And the limit here, cosine of x minus 1 over x. Again, if you plug in, you get another 0 over 0. But that's a known identity, and that equals 0. So we're actually getting 1 times 0 here, which is 0. Okay, still want to do two more. Number 6. Let's take a look at the limit of tangent of 10x over 5x. Plug in. Tangent of 0 is 0. You'd have to do sine over cosine, but you still get a big 0 over 5 times 0, 0 over 0. And now it's kind of tempting to feel, well, neither limit applies. You know, the first couple, we had sine x's, sine 9x, things like that, to kind of point us to the sine limit. Here, especially after we factored, now we've got that perfect cosine minus 1 to make us think about the second. But now we got a tangent. Well, one of our first, most basic manipulations of tangent. And notice, everybody, I hope you realized I'm writing the limit until I plug in. And our plug-in so far is basically use the identity. Technically, I'm not plugging in here. I'm using the identity, but the limit notation was there until I used that identity. That's when it dropped. Limit notation is there. Here I'm using the identity. That's where the notation drops. So right now, I'm not using any identities. I'm just manipulating, so I still have my limit, like we did from here to here. So I've got sine of 10x over cosine of 10x over 5x over 1, which if I clean up that fraction would give me this. The divide by 5x over 1 become a times 1 over 5x. Do we see it? Not obvious, but maybe now we're seeing, hey, let's group these pieces together. By grouping these pieces together, that'll give me the opportunity to apply this identity. So, still have my notation. Group those together. But I can't ignore the cosine. It's still there. It's still in the denominator. But I just want it out of my way. So I'm going to put times 1 over the cosine of 10x. Again, everything I'm doing algebraically, order of operations, using your operations, it all works. We're more accustomed to multiplying this and making this into this, and then maybe grouping sine and cosine to make it like this, but this is a legitimate move. These are equivalent. And now, here, sine u, well, I need that to be a 10x. I mean, this one, again, there's no harm at all. Push the 5 out in front, do a 10 over 10. But this one, maybe you might see it a little easier. If I multiply top and bottom by 2, that gives me my 10x. So the 2 pushes along. There's your identity, sine u over u. Combined, that gives you a 10x. So there's your sine u over u, which goes to 1 as x goes to 0. But don't forget about this. And don't say the answer is 2 over cosine of 10x. What do you do with this? You still have to plug in. So you get 1 over cosine of 0. Cosine of 0 is 1. So 2 times 1 times 1 over 1. This would have a final answer of 2. Okay, last limit problem. And then the next video, I'll do a little bit of proof with the derivatives, and then we'll get some practice. First, prove what are the trig derivatives, and then we'll get some practice. But one more, and I'm just going to squeeze it in the side here. What about the limit of sine x over x as x approaches pi over 4? Did you fall for it? A lot of people just jump and say the answer is 1 because they're applying this identity, but realize this does not apply. We're not in a 0 over 0 case, and even though you might say, but what do you mean it doesn't apply? It's got the perfect sine x over x. Don't underestimate or undervalue this part. This would be the identity if x approached 0, but it is not. This is not even a trouble problem. All you got to do is plug in. Sine of pi over 4 is rad 2 over 2 over pi over 4, and that may not be a pretty answer. It's not going to be too pretty no matter what. I guess the best you could do, if you multiply by the reciprocal, 4 over pi, the 4 and the 2 would reduce, so you get 2 times radical 2 over pi. That seems to be about the best we could do for that problem.